So, waves are a type of simple harmonic motion. So before we actually get into waves themselves, we're going to look at some other harmonic motions. And harmonic simply means that it's a repeating pattern. And so we're looking for things that have a repeating pattern of motion. The first of those is a pendulum. And a pendulum is simply a mass that's suspended from a pivot. Usually it's a mass suspended from a string or from a rigid bar, and then it swings back and forth. And to make life simple, we usually consider the string or whatever the support is to be massless. Otherwise, you have to use calculus and take the integral of the mass as you go up, and no one wants to do that. So anyway, period is the time it takes to make one cycle, and we can calculate the period of a pendulum using the following formula. The period of pendulum is equal to 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity, or g. And the units, of course, for a period then, since it's a time, is just seconds. Next, another type of harmonic motion are oscillating springs, springs that are bouncing back and forth like so. And so elasticity is simply the ability of a material to return to its original shape after a deforming force has been removed. So something deforms it, and then we take away the deforming force, and it restores itself. That's elasticity. Something like Play-Doh, when you deform it, doesn't bounce back. It's inelastic. Whereas something like a rubber ball is elastic because when you squish it, it will bounce back to its original shape. Things that don't deform much in the first place are actually more elastic than it turns out. So even a steel sphere is actually more elastic than a rubber ball because the deforming force doesn't deform it that much, and it restores its original shape very quickly, if not instantaneously. Anyway, this brings us then to Hooke's law, which is the guy up in the corner. And Hooke's law basically says that the distance the elastic object stretches or compresses, depending on what kind of spring we have. Some springs you apply a force to squish them, other springs you apply a force to stretch them. But the distance that it squishes or stretches is proportional to the force applied, and specifically is proportional by a constant called the spring constant. The interesting thing here, though, about the spring constant, though, is that it is a value unique to each spring. So it is constant, but it is unique to each spring, and so every spring has a unique spring constant. And if you take a spring and you cut it in half, the spring constant changes, though it changes proportionally, it turns out. And then, of course, as we've seen all year, because F equals ma, or Newton's second law, is true, we can substitute ma in for F, which is the more common version of the formula we use, that ma is equal to kx. And while we're on springs, a couple other spring formulas. First off, the elastic potential energy of a spring is equal to 1/2 times the spring constant times displacement squared. You'll notice that that formula looks almost exactly like the kinetic energy formula for a moving object. The difference is instead of mass, it's kinetic energy, or excuse me, spring constant. That's an important thing. Instead of velocity, it's distance. And here we're calculating potential instead of kinetic, but the format of the equation is the same. And we can also find the period of an oscillating spring. It turns out it's very similar to the period of a pendulum, and that is 2 pi times the square root of this time mass instead of length on top, and spring constant instead of acceleration due to gravity on bottom. If you have any questions, be sure to jot them down and bring them with you to class.